All right, to begin, the second lecture of the tutorial. So now that we've gotten the boring parts over with in the morning, I want to give the interesting part of the tutorial between now and lunch. So this is where we're going to change our focus just a little bit and think about engineering assumptions rather than assumptions that are about the way systems operate. Let's think about assumptions about the way people build systems. And as a vehicle for this, I'm going to talk about election systems, which is an area in which I've done quite a lot of work looking at real artifacts that people have built, real voting systems that democracies use as part of their core infrastructure. Election systems are particularly interesting from a security point of view because voting is a really, really challenging, kind of unique security problem. So normally in elections, we have a couple of different challenges we're trying to solve. We want, of course, to count votes correctly, that is, to ensure the integrity of the election outcome. We want to make sure the right people get into office as a result of the election. But simultaneously, we want to have this thing called the secret ballot. We want to ensure, in other words, that nobody can figure out how you as an individual voted, even if you try to help them. You try to prove it to them. And that last part is key, because that's what prevents you from being coerced. It's what makes it harder for you to sell your vote. If you wanted to prove how you voted to someone else, the secret ballot would have a much weaker effect. Now, this combination of requirements of integrity and ballot secrecy gives a very unusual shape to the voting problem. It makes it very difficult to apply security mechanisms that we apply to other things like e-commerce or banking in other areas of life to voting. And it makes it really interesting. At the same time, this is a critically important problem. It's, if you're talking about elements where computers are being applied in critical infrastructure, voting is certainly an application that should be on that list. Because if your voting system can be compromised, there's a tremendous amount of power and money that can flow in the wrong direction. So you might think that the engineering, the technology that goes in to creating computer voting systems is going to be top-notch. You might think that the election systems we depend on are going to be secure. Well, if you think these things, maybe you haven't been reading the right publications, because I'm about to tell you some very disturbing things about the state of practice. All right, so in the US, electronic voting has been around in some form since the 1980s, but it really took off after the 2000 presidential election debacle, which was, for those of you who don't remember, the case of Bush versus Gore, in which the outcome of the election, who was the next president, wasn't known for almost a month because of problems counting ballots in Florida, and where the eventual outcome had to be decided in the Supreme Court, which decided to order them to stop recounting and resulted in George W. Bush becoming president. After that, that was a national embarrassment that we had such a problem choosing a president. And after that, Congress finally acted and allocated a large pot of money, order $1 billion, to the states to upgrade their voting systems, to get rid of the previous technology that had been in use. The problematic ballots in Florida were based actually on manually punched cards. And most states use this money to upgrade to shiny new voting systems like this one, the Diebold AccuVote TS, computer-based touchscreen voting machines where all of the records of the ballot would be stored in computer memory. There'd be nothing to recount. It would eliminate any problems like the Bush versus Gore fiasco, and all would be well. Now, of course, as a computer scientist, looking at a machine like this, you think, well, internally, how is this going to be any different from a laptop? Or maybe, actually, architecturally, this particular machine is very similar to a Windows CE PDA. And we know that these other devices have all kinds of security problems. We know that people are able to hack into them. We know that they suffer from bugs. We know that they suffer from vulnerabilities. So looking at a voting machine like this, as anyone with an ounce of security skepticism, I mean, you know, you think about what could go wrong. And I think in the Diebold case anyway, many computer scientists did point to this and raise objections. Well, have you considered this attack, that attack? The manufacturer Diebold, which is famous in the US as a big producer of things like safes and ATMs, basically told the public, trust us. We've put the effort into making sure this is absolutely secure. Nothing will go wrong. But, oh, by the way, nobody is allowed to see how the machine works. It's a trade secret. Diebold was fantastically aggressive at trying to prevent anyone from doing an independent security analysis of their machines. They had passed minimal, superficial testing procedures that were mandated by the federal government, which basically consisted of having someone who was working for the manufacturer look at the source code and make sure there were no go-to statements and that there were comments. No real security testing. But the company actually threatened election officials who told them they wanted to provide the machines to third parties for an independent security assessment. They threatened them with lawsuits. They actually got somebody fired from his job who was another election official in another jurisdiction. They had contractual claims when you terms when you purchased one of these that imposed very strict confidentiality requirements. They went way out of their way to make sure that no one would look at one of these. Then, in about 2005, after years of computer scientists wanting to have a hands-on view of one of these machines, my group at Princeton was approached by an anonymous source who provided us with a machine to study. So this anonymous source, first of all, I won't go into who it was, but our lawyers assure us that the source was able to legally provide us with the machine. There's some great stories, though. So I was, back as a grad student, I was tasked with actually meeting the source and picking up the machine. And you can't make some of this stuff up. So I drove up to New York City in the big white sedan I had back then, and double parked outside of a Times Square hotel. And then I had to go into the alleyway behind the hotel, where a man in a trench coat was carrying a big black leather suitcase containing the machine. So this is the beginning of this long and wonderful story. So we had to work in absolute secrecy when we were examining the machine, because based on the company's history of litigation and threats against people who were studying it, we knew that if they found out before we were ready, they would do everything that was available to them to try to slow us down or stop us. So we spent the summer working down in the basement somewhere in a room that wasn't on the floor plans of the building. With no sunlight. We couldn't tell our colleagues what we were doing. We weren't going to announce until we were ready to go public that we were working on this at all. So we reverse engineered the machine, though. And it's really, I find it fascinating that this sort of thing is possible, but you can go and look up the data sheets for the chips and figure out how they work and trace the paths on the motherboard and basically go from no blueprints to an understanding of how the computing device works. And in the case of the Diebold machine, it's really a pretty simple embedded system. It's very similar to a, It's very similar to a Windows CE device, as I said. So what you have here, you have, I believe this is the CPU, These are the flash memory chips that store the system's internal software. It also has here an external PCMCIA card slot. And this is the slot that's used to first load in the design of the ballot before the election, and then after the election, offload a copy of the votes. The machine also has a little cash register style printer that prints out the local totals, and that gets signed immediately after the election and then lost somewhere probably. I don't know if that's routinely double checked. Similarly, we reverse engineered the machine's software using IDA Pro, which is a very powerful professional disassembly tool, figured out how it worked. After a long summer of working on this, we had a series of findings. And here you see our machine running a test election we've configured. So let me tell you about the first finding. So the first thing we found was that not only were all the records of the vote stored in the computer's various non-volatile memories, but they were all directly under control and permanently under control of the election software. So the way the software stack worked, you have a stock Windows CE kernel, basically the Windows operating system light, and then an application that runs on top of it that is the voting user interface. It's something called Ballot Station.
The software wasn't encrypted?
No, the software wasn't encrypted. You'll see more about the level of sophistication involved in a minute. But there were two primary places votes were stored, one in the internal flash memory and two in the removable memory card. They had redundant copies of the votes. So the first finding was we could just write our own application, run it on the machine, have it sit alongside the software that was counting the vote, that was running the election, and have it change the records of the votes every time the real voting software did to alter the results. So here's a picture of our application. It presents a very easy-to-use user interface. You pick who should win and by how much. Now, of course, a real attacker would not have this GUI on the voting machine, but you get the idea. So the software then changes all the records, changes the audit log to make the machine's output match what you ask for. Some of this stuff is encrypted. It's trivially encrypted. At the time, the encryption key, earlier the encryption key had been hard-coded, but they had fixed that by the machine we got. Instead, the encryption key was changeable, but it was stored in a file on the voting machine that was itself encrypted with a hard-coded key. So computer scientists like to add indirection, right? So that's how they solved this problem. But what could they do? This was incredibly easy. So based on this, we can give a demonstration. Our mock election we like to give so as to be as non-political as possible, at least domestically in the US, is George Washington versus Benedict Arnold, the traitor of the Revolution. Of course, we run this election. Maybe we have 5 people vote. Everyone votes for George Washington unless they make a mistake. And then at the end of the election, the machine prints out the totals. And oh, Benedict Arnold always wins because our ballot stuffer is running. So we gave this exact demonstration on live television on Fox and CNN one morning back in the fall of 2005, I think it was. And you wouldn't believe how nerve-wracking it is to demonstrate something like this on live TV. You're going to actually have the TV presenters cast the votes on camera, and then the machine is going to print something out, and either your attack worked or it didn't, and you look like a fool on national television. So the night before we were going to give these, Ari Feldman and I are there in the lab testing. And the philosophy behind this, what my advisor taught me that you have to do for this kind of demo, is appease the demo gods before, which means you do the exact demonstration you're going to do twice immediately before the real demonstration. You have to do it twice because that way you're also testing the reset procedure that puts it back into the state for the next iteration of the loop. And the night before the live television demonstrations, what we found was it worked most of the time. It was a very long night to make it work all the time and to figure out why it wasn't working all the time, but it eventually worked correctly on live TV. The second finding, all right, so the first finding, software installed on the machine maliciously can easily change votes. The second finding is that we can install malicious software easily with only a few seconds of access to either the machine or its removable memory card. And the reason for that is that the manufacturer left a trivial backdoor essentially to allow them to do software updates. If you have a file on that memory card with a particular file name and have that memory card in the machine when it's turned on, it will replace its software with the contents of that file with no authentication. Not even a confirmation prompt. Okay. This is the most widely used voting machine in the US at the time. Third finding is, based on that, we're able to construct a voting machine virus that spreads from one machine that's infected with the virus to, over the course of an election cycle or two, all of the machines in a whole county or state. So here, you have an infected machine, put the memory card in, it puts the update file on it. Maybe next you put the card into the next machine to offload the votes from that one. The card infects the machine. Through standard documented procedures, we know that this style of viral propagation is feasible. In later work, we've demonstrated even faster propagation, but this gives you an idea. All right, so infect one card, and these memory cards and voting machines in the US are not stored under really high security circumstances all the time. For instance, in many jurisdictions, the night before the election, they're left unattended at the polling place, like at the local elementary school or something, because they don't have enough people to watch all of them, and they don't have enough trucks to drop them all off in the morning. Or maybe they spend the night before the election at a poll worker's house. So conspiracy size 1, one person who wants to tamper with one of these, thanks to viral propagation and the power of computers, can change the outcome of a large-scale election. Okay, so this seems pretty bad, right? But there's one thing I'm not telling you, which is they had one safeguard, which is there was a physical door on the side of the machine that protects access to that removable memory card slot. So at least if you didn't have access to the memory card, you could hope that the machine would be secure enough to last until after the election. You guys think they're going to get this one right? So there are a few problems with the memory card slot, and I think this is an analogy for really the security and the level of engineering that's applied to this whole voting system and just about every other voting system I've seen. First problem, this physical lock uses the same key in every AccuVote TS machine ever manufactured. So including every voting machine in Maryland, every voting machine in Georgia, even to this day, same key. Okay, that's probably bad. Second problem, even if they use different keys, it's a really cheap filing cabinet style lock. It's trivial to pick. I can get it open in about 5 seconds with a set of lock picks. I've taught many students to be able to open it in 30 seconds with a pair of paper clips. Okay, high security once again. Third problem, so we looked at the real key, and there's a certain number written on the side of it, C415A, something like that. If you put that into Google, you start getting hits. Most of those hits are eBay listings, but they're not eBay listings selling keys for voting machines. They're eBay listings selling keys for jukeboxes and hotel minibars. It's a widely used standard key for all sorts of other low security applications. We bought one on eBay. I have it on my keychain. I just carry it with me. Here it is. It works in the real voting machine. If that wasn't bad enough, Diebold has a website where they sell replacement parts for voting machines, which has an online store. And one page on the online store is this, where they're selling the key. But wait, I have to give them some credit. They wouldn't sell it to just anyone. You had to have bought voting machines from them. You had to have a real account. But these black bars here, I added myself. Their real online store page had a very high-resolution picture of the key. One guy who was reading our blog posts about Diebold noticed this, went out to the hardware store and bought some blank keys that were, he thought, approximately the same shape, filed them down in his garage to match the picture and sent them to us, and they opened the real voting machine. So they were giving out, here in their online store, the only secret that was actually offering any protection to the real voting machines. That's the level of security that their engineering prowess was achieving. This is not, you talk about wanting defense in depth in security. This is weakness in depth. There's not one way to bypass the system. There's a half dozen ways to bypass the system. The attacker gets to pick and choose. All right, so that's Diebold for you. But you might say, you're probably saying to yourself, okay, so this is just one company that really screwed up. Well, how can we draw any kind of scientific conclusion from one incompetent company? And I would agree with you. This is an anecdote. This is just one data point. But after this study, in later work, we got to look at a lot of other companies too. In particular, in 2007, the Secretary of State of California, Deborah Bowen, commissioned a first of its kind study. She brought together academic researchers from across the security community and commissioned a study of the security of every electronic voting system used in the state of California, which California pulls a lot of weight in the US when it comes to regulation of different kinds of technology. So she was able to, using California's buying power, to get the voting machine manufacturers to provide source code, basically telling them, you'll let us study your voting machine or we'll ban it from California. And so almost every major voting machine manufacturer complied, and their machines were subjected to very detailed physical and source code analysis. So I got to be part of the team that examined the broader Diebold system, other machines they made, and so forth. Other teams investigated systems from other major manufacturers, including Hart and Sequoia. So what did these studies find? In the case of the Hart system, the study found possibility for malicious software to be introduced and change votes, and also, interestingly, possibility for election officials to violate everyone's secret ballot. The Sequoia system, the team found the same two problems. The Diebold system, we confirmed the same kinds of problems as well. Every one of these systems had the same level of severe engineering problems and vulnerabilities that we had found in the initial Diebold system, even though they were independently developed, different architectures. The one thing that made all of the systems similar, though, was the complexity of the system. If you'll believe it, each of these voting systems had on the order of 1 million lines of code, plus a stock operating system kernel. Why you need that level of complexity to run an election? Well, there's some arguments. To support things like accessibility, large format ballots, international languages, the very different rules that different jurisdictions have. If you're not thinking about trying to minimize complexity from the outset, then probably the fastest way, the first thing an engineer is going to think about is to use stock systems to build it the way you'd build any other application, to build it as if you were building Microsoft Word or something. And that's what they did. But the resulting applications end up being so complicated that if they were completely secure, in the words of one of these reports, if they were completely secure, they'd be probably the first system of that complexity ever to be fully secure. So that's what we were left with. But those aren't the only systems I can give you as examples in support of this thesis of widespread insecurity. All of those, by the way, were banned in California as a result of the problems we found. In Europe, they had experience with, in the Netherlands, with the NADAP ES3B voting machines, another kind of embedded system-based DRE voting machine. And Rob Honkrijp, who you see here, a good friend of mine, did a study of these machines where they found, well, they could reprogram the machines. In that case, it involved opening them up and changing a memory chip, but that was something they showed they could do in less than 60 seconds. Furthermore, and this is really interesting, these machines had a side channel where they had radio emanations that would reveal which candidate or which party was being voted for. So you could sit near them with a receiver and know who the person was voting for. So they weren't adequately protecting the secret ballot. He ended up reprogramming them to play chess, and the Netherlands no longer uses electronic voting. Back in the US, Andrew Appel, the chair of CS at Princeton, got really interested in local voting issues in New Jersey and bought on eBay a series of the same voting machines that they use, these huge, almost refrigerator-sized Sequoia AVC Advantage machines. These are older technology. Rather than a touch screen, it has a big board of switches. And in some jurisdictions in the US, we have this requirement that the whole ballot needs to be presented at once. You can't have multiple pages. And in places like that, this ends up being the easiest technology to use, even though it's ancient Z80-based stuff. I worked on a study with Hovav Shakam at UCSD and Steve Checkaway, who's now at Hopkins, to look at these AVC Advantage machines and ask the question, what are the challenges going to be like for voting machines as they age? Because you build a machine like this today, it's going to be expected to have a 20, 25-year service life. We know that attacks get better. How likely is it that the design of these machines is going to be able to survive? So we reverse engineered the machine using significant grad student labor to trace through every path on the motherboard, to reverse engineer the software once again. One thing we found that was very interesting was that the designers of these machines had implemented a pretty sophisticated kind of protection against rogue code running on the machine. They had a hardware circuit that did memory protection that made sure the machine could not execute any instructions that were loaded from volatile memory. So say if you tried to do a buffer overflow, the processor would halt. And this is today a standard feature in modern OSs and CPUs. It was way ahead of its time that way. But now attacks have also gotten better. And we have this idea called return-oriented programming that is designed exactly for circumventing that kind of protection on standard general-purpose PCs. Return-oriented programming works by, rather than introducing new CPU instructions following a buffer overflow, you insert a series of return instructions that call snippets of existing code in order to form essentially a Turing-complete instruction set based on rearranging existing snippets, the way you might rearrange magazine headlines to form a ransom note. We were able to demonstrate return-oriented programming in the extremely confined operating environment of this AVC Advantage voting machine. And we're able to use this modern attack to circumvent its 1980s, advanced for 1980s defenses. So I think this is a real worry for machines, even if they're designed well now. How are we going to be able to argue that they're going to be able to cope with advances on the attack side 20, 25 years from now, in virtually unthinkable time horizons for computing? All right, so that's a lot of examples of voting machines with problems. Just one more. So this is a couple of years ago. My old co-conspirator Ari Feldman and I were approached by a friend who had bought on eBay yet another US voting machine that's still widely used in a number of states, something called the Sequoia AVC Edge. This is another touchscreen machine. And by this point, we were old and jaded, and there's not much more we're going to learn scientifically by reverse engineering another voting machine, but we couldn't help but open it up and take a look, at least on a weekend sometime. So we opened it up, and it's a big suitcase kind of thing, and took a look at the motherboard, and hey, what's that up there? Well, look, it's a compact flash card, like in your camera. I wonder what's on it. Well, it turns out it's the voting software is running on it. And hey, the CPU is a 486. I remember that. Well, being good geeks, the first thing we did was run Linux on it. So we could just reformat the compact flash card. It's running a standard compact Linux distribution here. The second thing we did was run Doom on it. Although, our necks started hurting pretty badly after a few hours of playing Doom on the voting machine. So eventually we found the perfect application, and I think a great use for all of the DRE voting machines that are now, should be thrown out or repurposed because they're not suitable for use in voting. We made it into a Pac-Man machine. So this is running the original 1980s Pac-Man in emulation on a voting machine. This is, I like this as a demonstration because if we can make it play Pac-Man, people understand, we can probably also make it steal votes. All right, so that's chapter 1. But most places in the world, however, most of the world's democracies don't look that much like the US and Europe. Even though almost all of the research that's been done in electronic voting has been focused on the problems the technology used in jurisdictions in the US and Europe, most of the world's voters vote in places that look more like this, like India. India is absolutely amazing. I mean, they're the world's largest democracy, right? They're also the world's largest user of electronic voting. Not many people know this, but India has been using for at least 10 years a homegrown, domestically developed electronic voting system that's highly tailored to the specific context of Indian elections. And India's long been one of my favorite countries to visit. I mean, it's just amazing. Amazing to be there and to see the levels of diversity, the levels of difference, and frankly, compared to the US scenario, of totally different perspectives on things. And I think the perspective that you get from examining their voting system is also a fascinating and telling one about the nature of electronic voting. So let me tell you a little bit about their voting system and sort of the requirements it tries to satisfy. So rather than build a complex system resembling a PC or a very powerful general-purpose computer architecturally, India's engineers developed a very inexpensive, low-cost, special-purpose embedded system for the purpose of voting. The system consists of 2 units, a ballot unit and a display unit, that are connected by, I think, a 3-meter cable, something like that. The voter interacts with the ballot unit, and the poll workers interact with the control unit. So contrasting this to systems used in the US and Europe, the Indian system, much simpler design, much more of an embedded systems velocity, much lower cost, much less complex, many orders of magnitude smaller code base. We're talking about thousands of instructions rather than millions of lines of code. Our research shows that the Indian system is also vulnerable, but to different styles of attacks than the US system. So to give you a little bit more of a view into the system, because this is important, and I should couch this a little bit by saying this is a beautifully engineered system, given the constraints of the problems India faces. really, really, really well engineered, but they got the specification wrong. But let me show you a few things that they got right. So India, they have to deal with people who speak so many different languages, so many different scripts, such a low level of literacy, unfortunately. So there's a party symbol for every candidate, and they advertise these. You don't need to be literate to use one of these machines. You also don't need more than the lowest possible level of technological literacy, because remember, there are places in India that haven't been electrified. There are places where probably there are voters who do not, on a daily basis, deal with any form of technology, any form of electrical device. So the interface for the voter is to press one button. You press the button next to the candidate you want, the machine beeps, that little arrow lights up, and you're done. Would be very hard to simplify this process further. On the control unit side, also really fascinating. So because the machines have to operate off the grid most of the time, it's completely battery powered. It's not a backup battery. The battery is the power source. The machines are not networked. There's no I/O except for a display and some buttons. So that makes the attack surface much, much smaller, but it also makes it so that the machines can operate independently in the field without any kind of programmer or offloader. This design, I love this part of the design. It's the physical design here of these buttons, and what you see here, these are a series of doors, of nested doors that close over them and are individually sealed. It basically models the state machine of the election process. So the different phases of the election, before the election, zeroing the machines, then going into voting mode, then you have the votes stored in the machine, but you're not ready to count, then you've counted them and are just storing them ready for the next election. Each of these is physically manifested with a different combination of these doors being sealed or the seals being broken, and different buttons to execute these different functions are available at different points in that process. And then the counting. And this is another beautiful, beautiful ritual. So the machine displays the election outcome by lighting up these 7-segment LEDs. And here is and what it does is it cycles through each candidate number and says how many votes that candidate received. And there can be up to 64 candidates in one of these configurations. So here you see it's going to show the total number of votes, the number of candidates, and then for each candidate number, how many votes they've received. And the way counting works in India is, and this might be a couple of weeks after voting, because elections are long processes over a period of days. But a couple of weeks later, it'll be time to count, and they'll get interested people together into a big hall, maybe a room like this, and they'll go through each voting machine and hold it up in front of everyone, and then press the button that reveals the votes, break the seal, show the totals. Everyone can see what the machine is outputting at the same time and write it down themselves and have an independent record. I love that. It's just, in terms of a simple way to solve that problem, there's a lot to like about that. Okay, so even though the machines have a lot of positive engineering features, the government officials who were in charge of elections in India, the Election Commission of India, which is basically an independent government body like the Supreme Court, started making claims that went a bit too far. For instance, they claimed the machines were infallible. They claimed they were perfect. They claimed they were tamper-proof, period. That there was no need for technological improvement at all. And of course, these are laughable claims, right? Because there's no engineered system, no system built by man that has these properties. But in serious debate in political context, they would make these claims. And you sort of see what they're trying to do. They're trying to allay any doubt that voters have. But look, if we're going to have a reasoned debate about technology, we can't have the people, the only people who have access to the technology, by the way, it was a secret once again, and they wouldn't let anyone else independently study it. We can't have the people who have the only access to that physical artifact making claims that are not true. And people in India started to have their doubt. There were, after a particularly close presidential election, a large number of people started to suspect that maybe the machines were not as infallible or as accurate as claimed. Some even tried to approach the Election Commission and ask them to do an independent security evaluation. In particular, a man in Hyderabad named Hari Prasad, who was a self-taught high school dropout who went on to teach himself engineering and found a small company that did electronics prototyping with embedded systems. Hari, through a weird chain of events, ended up becoming one of the leading technological critics of the voting machines in India, and actually was invited at one point by the Election Commission to go to their headquarters with his team of engineers and get to open up one of the machines and take a look at it. When they got there, they opened it up and started poking around and said, "Oh, haha, this is going to be much easier to tamper with than we thought." At which point the Election Commission workers standing there basically ushered them out of the room. "Hold on, we're going to have to think about this trial a little bit more." And invited them back a couple of weeks later under new conditions. If they could demonstrate tampering with the machines, the Election Commission would admit that they were not infallible, but they could only demonstrate normal tampering, quote unquote, where normal tampering was defined to mean tampering with the machine without opening it up or knowing how it worked. Okay, so that was the state of affairs in India when I got involved, which was about February of 2010, when Hari Prasad in Hyderabad was approached by an anonymous source, a government whistleblower, who agreed to give him a machine to study under conditions of anonymity. So Hari ended up inviting me and Rob Honkripe, the guy who hacked the NEDAP machine and made it play chess, to come from Europe and come from the US and join him in Hyderabad to help do a rigorous scientific study of the machine from the anonymous source. So we opened up the machine and reverse engineered it once again, and I don't know what the big secret was that the Election Commission was trying to keep, because when we published these pictures, this was the first time Indian citizens ever got to see what was inside the machines that determined who their national leaders were. But it's really very simple. There is a simple embedded CPU with the software burned at the fab, already baked into it, a couple of very small EEPROM chips that store redundant copies of the votes, and that's pretty much it. These huge things here, these are the micro switches underneath the buttons, so that gives you an idea of the scale. There's only one other thing in the control unit, which is this daughter board here, which has these 7-segment LEDs, and it's just LEDs and wires. There are no active components whatsoever. So the story is a little bit more complex. I actually found out that Hari had a voting machine 5 days before I was already scheduled to visit India to give a talk with some other people about voting security. And it was only a few days in advance I found out we were going to actually have access to one of the Indian voting machines to do tests on, to study. At that point, with just some grainy photos and some sort of hand-drawn diagrams from oscilloscope readings, I tried to think about what the simplest attack we could do and actually demonstrate in the field would be. So there are a few things you might think about, but what I came up with then on the phone with the Indian team was to try to attack this part, the display board, and to try to come up with a way to tamper with that part to jeopardize elections. Now, we're talking about a very different attack than software tampering. Right now we're talking about hardware tampering. And is that a realistic attack? Well, there are a couple of things about the Indian election system that make me think maybe it is. One is that these machines, India, by the way, in the last parliamentary election, used something like 100,000 voting machines to count something like 500 million votes. An incredible scale that the system is on. And there are warehouses across the country where these machines are stored. And there are thousands of voting machines in each warehouse. Most of these are not high security facilities. It's like it's an old warehouse or the basement of the high school. Maybe there's a night watchman. Maybe he makes $1 a day. Maybe he won't. Maybe you can tell him what you're going to do to his family if he tells anyone that you got into the room where the machines were stored at night and spent the night there with your team of goons. So you can imagine ways that people could get physical access. The machines are protected with seals, but this is what the seals look like. Candle wax and string. Maybe some of you, I'll leave it as an exercise to the audience to figure out how you might tamper with seals like this. Okay, so we're going to try a hardware attack. First problem I have is that what I know about circuits, I'm a professor of electrical engineering, but what I know about circuits I learned from a children's book when I was 5, so I have not the first clue about how to build a circuit board. So I went down to my graduate security class and basically polled the class. Does anyone here know how to make a circuit board? Oh, by the way, it's Thursday afternoon. I need it on Monday. So Eric Woostra, this guy you see here, the telex student, sheepishly raised his hand, and that's why he's now my student. So over the next 2 days, Eric designed from scratch and had fabricated a board to carry out this attack. This board at the top is the one Eric built. It looks almost identical to the real display board in the real Indian voting machines. Except underneath those parts, we've added some new chips. This is a CPU. It's a little embedded microcontroller. And what it does is it intercepts the lines that are driving those LEDs, decodes what vote totals the machine is trying to display, and heuristically shifts votes to other candidates based on a target candidate from the attacker, so that the target candidate gets more votes, but they still add up to the same overall total. And it does this as the machine is trying to show its output. Here are a couple of pictures. This is next to the real one. We could make the color a little better if we did another construction here. And you can see that they are very, very difficult to distinguish. Just have one problem left, which is a real attacker who did this. You break into the warehouse. You want this tampering to be good, not just for this election, but for every future election in which the machines are in use. But you're not going to know 10 years from now who's going to be, which number your candidate is going to be. Are they going to be candidate 1 or candidate 5? So we need some way to signal to the machine who it should cheat in favor of. And we thought about a bunch of different signaling mechanisms. Maybe there's some neat things you can do with the procedures to signal by the number of candidates, which the attacker could have some control over, by a secret knock, a combination of a sequence of votes or something. But what we ended up doing is why this chip is here. That's about the size of my thumbnail, and it's a Bluetooth radio. We built this app that someone standing in the room while the counting is being done can use to send a signal to tell the machines, to tell the dishonest displays who to shift votes in favor of. So we conclude from this that tamper-proof is an overstatement. All right, but now we implemented a second attack too. And this is looking at these chips. These are the EEPROMs that are storing the votes. So the team in India hooked them up to a logic analyzer, and we're able to pretty easily figure out the data format. Remember, this is a very, very simple machine, and one of the things that they simplified was they didn't do any cryptography. So the votes are stored as an array of bits in these EPROMs, and there's some redundancy, but you can figure out the format. And of course, if you can get the machine into the laboratory like this, you can use that to tamper with the votes. But we wanted to see how practical it might be to do tampering of this sort in the field. So instead of, so here's the scenario. India, for many years before they introduced electronic voting, had a problem called booth capture. And this is probably something that makes India different from Israel or Europe or the US. So the problem was some rural election place, everything would be fine on voting day until a car would drive up and a squad of goons would get out working for some particular candidate. And goons is the technical term they use in India for whatever reason for this, I understand. They'd take over the polling place, basically tell everyone to go home and proceed to stuff the ballot box. Maybe eventually the police would show up. Probably not for a long time. So to try to counter against that, the electronic voting machines only accept votes at a limited rate, maybe 1 per minute. And that's their defense against booth capture. But can we come up with an electronic form of booth capture? So if someone takes over a polling place with these EVMs, if someone gets access to them between voting and counting, can they stuff the electronic ballot box? Here's what we came up with. I call it Clippy. Clippy is a little handheld device, costs about $20 to build, clips onto the memory chip inside the machine with the machine powered off, drawing its power from the machine. And Clippy has a little CPU on the underside of that board, and will reprogram the ROMs in the EPROM in the machine to shift votes to the candidate number that you pick with the number on this knob. So if you want to shift votes to candidate 2, you set the knob to 2, clip it onto each of the chips. The little orange light lights up to let you know it's working. Then the little green light lights up to let you know it's done. About 2 seconds later, you move on to the next machine. So this is so simple. Because of the simple design of the machine, the physical attacks are proportionally simple in this case. We can build these things very inexpensively. There are, I think, at least 1 million electrical engineers in India who could implement the same attacks, probably better than we could. You can build it simple enough and low cost enough that your unskilled goons can carry out the attack in the field. I think this is a realistic kind of threat in the Indian context. And then there's the software that actually runs on the machines in the official chips. So we never did get to see what that software looked like because the chips are designed so that they're, once they've been programmed, you can't read the software back out. In this case, that also means that once they've been programmed, you can't verify the software that's been programmed into them. What that software does, basically adding up button presses, should be pretty simple, but of course it would also be pretty simple to add some backdoor, so if you pressed a certain sequence of buttons, they'd shift votes. And turns out the election officials, the government, doesn't own the source code to that software that really counts the votes. In fact, they've never seen the source code, they tell me. In fact, the government's chief scientist told us at a conference that, quote unquote, only 3 or 4 guys at the companies that wrote the voting machine software know what's in the code. This is absolutely incredible to me, especially if they can't read it out and verify it, that only 3 or 4 guys know what's in the software that's counting Indian, that's determining the outcome of Indian elections. If you know who those 3 or 4 guys are, and you want to change the outcome of those elections, there are 3 or 4 guys who you have to get not to talk about the fact that you bribed or coerced or threatened them into putting a backdoor into that code. So we conclude from all of this a few things. So India's voting system is not secure. There are simple, low-cost attacks that can be used to tamper with the voting machines. Fraud is not rocket science. This is something that's accessible to people with basic technical skills, yet it could be very difficult or almost impossible to detect, depending on how well it was executed. And this isn't merely hypothetical. So Hari Prasad, the guy in Hyderabad, was after our study came out, he was approached by one of the regional parties and offered a large pot of money and access to the warehouse if he would help them to cheat in the next election. Now, he sent those guys packing. I mean, he's working for the good of his democracy. But still, I mean, it really makes you think that, I don't know about in every country that practices electronic voting, whether this is the easiest way to tamper with elections or something that would really happen. But I worry quite a bit about India. So we published these results at CCS in 2010. Simultaneously, Hari went on TV in Andhra Pradesh and gave live demonstrations with our machine from the whistleblower of these tampering possibilities that we had demonstrated. And this kicked off some amount of debate in the Indian media and Indian political society. The Election Commission shot back first saying it wasn't a real machine. Then even if it was a real machine, it was stolen, which I don't think it was stolen, and I don't see how that invalidates the results. It took a long time for them to come around to accepting the claims. Meanwhile, a lot of people became increasingly skeptical. Unfortunately, we started seeing some stories like this that were rather disturbing. Intel background check on EVM thief. This is accusing, this is in the Times, which is the paper aligned more closely with the ruling government in India, and it's mentioning that it goes on to basically accuse Hari of stealing the machine, but also says it got technical help from 3 foreigners, a part of some larger conspiracy to discredit India's election process. So accusing there being a foreign conspiracy. So this made me a little bit worried. But then one day, 2 years ago, a little bit after, just after Usenix, Hari received a knock on his door in the middle of the night. It was the police. There were about, I forget what he said, something like half a dozen officers came into his apartment, woke up his family, and told Hari he was under arrest. He was going to be taken across the country to Mumbai by car to be questioned about the theft of the voting machine. The officers also told him, he said, "Just tell us who gave it to you, and this will all go away." So Hari really is an amazing fellow. What he said, and I got to talk to him by phone as he was being driven across the country. They were very nice. They gave him an air-conditioned car for the 14-hour car ride. He told me, and you can find this phone conversation online, I recorded it, "I can't tell the police who gave me the machine because if I do, what whistleblower is ever going to trust a technologist or an activist again? I have to maintain the promise of confidentiality because that's the right thing to do." And so he did. And even though they kept him more than a week without a lawyer and questioned him every day, even though it was more than a month he was held in detention in Mumbai at the police station, away from his business, away from his family, Hari did not tell, and has to this day maintained the anonymity of the source. I have met the source. I know it was not stolen. It's an amazing, amazing story. Hari eventually was brought before a judge who told the police to let him go. This man has, if anything, done a service to his country. You have to investigate the claims, not the source. So this process, Hari's arrest, resulted in a kind of sea change in India. So the debate shifted quite a bit because of the amount of publicity this generated. And almost miraculously, in October of 2010, there was an all-party meeting where all the political parties came together in India. They called on the Election Commission to actually investigate and address the problems we found. And at that point, the Election Commission's attitude changed completely. Rather than trying to make the problem, to dismiss the problem, they started working with Hari to make it go away. And the election commissioner thereafter was on a first-name basis with Hari, exchanging text messages several times a week. It's incredible. Today, India is finishing field testing of a paper trail add-on to the electronic voting machines that will provide a physical record of every vote that can be independently maintained and independently counted, a way to check that the electronics are functioning properly, a way to verify that the votes have been stored correctly. So this is the direct result of, I think, Hari's risk-taking and amazing ability to put his engineering prowess and his political abilities together for the good of his country as he saw it. Sometime after this, I tried to go back to India, and they tried to deport me on arrival because I was apparently on the files as part of a foreign conspiracy to destabilize the country. It was ironic because I was going back to meet with the Election Commission to try to help them with their new field trial. Really ridiculous series of events for another time, for another talk. Eventually, after getting almost the entire Indian government involved, I was allowed to enter the country. But after 24 hours of detention at the airport, and after a story like this appeared on the front page of the biggest English language paper, announcing that I had been deported. So, long story for another time. All right, I want to turn to one more topic before we break for lunch, which is internet voting. So, can we safely vote over the internet? The answer is no. Some of you in the audience may dispute. We'll let Tal and Alon have their thing to say about it, but there are some serious, serious challenges to voting online. I mean, just think about it. If the level of engineering that's going to go into online voting is anything like the level of engineering that went into offline voting, how are we ever going to build online voting systems that are secure? Furthermore, the problem is even harder than voting offline, because suddenly you're connecting your voting system to the internet and you're facing potential adversaries from anywhere in the world, including, increasingly, what we're worried about in other kinds of critical systems, state-level attacks from sophisticated foreign governments with substantial resources. You also have to worry about the security of the voter's PC, which is something, at least with the offline voting systems, you can imagine that you have some level of control over the whole system. With online voting, now you have to worry about the voter being phished, the voter having malware on their computer that tries to sit between them and the election server, the voter already being part of a botnet where someone could just rent time on the botnet in order to try to shift votes. So I want to just talk about one example of internet voting, which is probably the best scenario we've seen so far, where someone has built an internet voting system intended for real use in a real binding election, and then it's been studied publicly. There are other countries that use electronic voting, like Estonia has used electronic voting in real elections, but their system until just a couple of weeks ago was closed source. And it would be a crime to really try to probe it on election day. The one case where we really do have good evidence and a good anecdotal description of a security analysis is from Washington, D.C. in 2010, where Washington, D.C., the city government got federal money to prototype an internet voting system that would let voters living overseas or voters in the military cast their votes through a website. So Washington, D.C.'s very progressive election officials decided to go to the computer security research community and ask us, well, how should we build our voting system? And what almost everyone told them was, no, no, don't build an internet voting system. We don't know how to do this securely yet. You're going to get hacked. But they wanted to do it anyway, so they did. They went ahead and built it. But to give the research community an opportunity to put our money where our mouths were, they basically said, we're going to hold a public trial, a mock election, 2 weeks before the real election. And anyone in the public who wants to hack into the system and show us that it's insecure is free to do so. Well, it's not every day you're invited to hack into federal government computers without going to jail, so I couldn't resist. So I put a team together at Michigan to take part in this trial. Now, their system was pretty well designed. They applied a lot of, from an engineering perspective anyway, from a crypto perspective, it's primitive, but from an engineering perspective, they're doing a lot of things that are considered best practices. They have multiple rounds of firewalls and intrusion detection, and everything is virtualized and rewindable, and it's written with type-safe language. It's Ruby on Rails. It's popular, Linux-based, LAMP stack, what have you. Here's what it looks like. It's very, very pretty. The voter goes to the city website, checks in they're authenticated using a PIN that's sent to them in the mail before the election. Thereafter, the voter can download their ballot. Their ballot is a PDF file, and the reason they did it this way is these were going to just be printed out and then counted with the rest of the mail-in ballots after the election. So the voter fills out their ballot in a PDF reader, goes back to the website and uploads it, and then the system thanks them for voting and tells them they can tell other people about it on Facebook and Twitter. So really cool, high-tech, modern. Okay, I see why people might like this, but is it secure? So my grad students and I, and none of us is a professional hacker. This is not even what we do in our do for fun most of the time. We decided we'd have a hand in this. So 2 weeks before the election, they make the source code available. And this is a great thing, because this is really the only realistic way to do penetration testing, is to let the testers have access to the source code. If you're talking about sophisticated bad guys, you have to assume that they've already broken into your development team's servers and stolen the source code. So they released the source code, and we spent a bit of time poring through it, probably a late night. Actually, none of us had ever read Ruby before, so it was quite painful. So after a few hours of looking at the source code, basically concentrating on the attack surface, the parts of the source code that data the attacker provides might be touching, that the attacker would have some way to manipulate, we hit on this line here. So what this line is doing is it's applying GPG, a standard crypto tool for doing public key encryption. And what it's doing is it's taking that PDF file the voter uploaded and encrypting it with a public key, the corresponding private key to which is stored offline somewhere. This is ensuring the ballots can't be read until it's time to count them. One thing that caught my eye was here, where it's adding to the GPG command line the path to the uploaded ballot. They're using double quotes instead of single quotes. Right there. That was enough to let us change all the votes and steal the election. Here's why. All right, so this enables an attack called a script injection attack. So the file name that's being uploaded, in this case because of the library they were using, was only partially sanitized. The base name is replaced by a random string, but the file extension remains the same. So if I upload a PDF file, it will be processed as a PDF file. If I upload an XYZ file, it's an XYZ file. If I upload a $, parentheses sleep5 file, it's a $. Wait a minute, that's not a valid file name in Linux. In fact, what this does in a shell at Linux, in something like bash, is it causes a subcommand to be issued and that string to be replaced by the output. So this is going to execute the command sleep5. If you upload a ballot with this name, you'll notice that the server returns an error message, but only after a 5-second delay. That's how we actually confirmed the problem. So this is the basis of our shell injection attack. The double quotes, had those been single quotes, it would tell bash or the shell not to execute any subcommands in that string. They used double quotes by mistake. It was a fatal mistake. That wasn't the only mistake they made, though. So we looked at the rest of their network. This is all before the real mock election starts. We look at the rest of their network and probe it, tools like Nmap, find out what else is running. We found several other interesting devices on the same network segment that they told us was going to be the election server. They said, this network is in bounds for the penetration test. One of the things we found was something called a terminal server. This is a device for remote administration that basically gives you, lets you log in over the network and then get serial console access to other devices like routers or switches. Remote administration tool. We identified the model using Nmap and then Googled for the manual, and hey, the manual has a default password in it, and yep, that works. They left the default password on this. Simple mistake to make. Except after we had a default password for this, we could install a backdoor on it that would let us look at all of the keystrokes they were using to configure all of the other systems on the network, and we were able to sniff all of the administrative passwords that way, including the backdoor, the root passwords for about, I don't know, a couple $100,000 worth of Cisco gear that was going to go into the city core network and was going to be touching all the subsequent packets that were going to go to the real election system. That wasn't so good. So I could sit in my office here in Michigan, watch their keystrokes in real time, while simultaneously, elsewhere on the network, we found these cameras in the data center that didn't have any authentication that let us watch the people in real time. As they were setting up, here's the systems, the servers running the election system. We could see if they were making any changes. We could also, and I love this, we could see the demeanor of the sysadmins. And that gave us a good clue about whether they were on to the fact that we were hacking into the system. So before the election, they're calm, they're normal, they're going about their job. Here's the night watchman who can't tell by looking that we've hacked into the boxes. After they eventually did find out that we had hacked into the system, these guys burst into the room and were not very happy. So this was very valuable information from the attacker's perspective. Okay, but the attack hasn't happened yet. This is all, background and preparation and lead up to it. The actual attack, we waited, based on what we had learned by observing the election officials, we waited until after 5 o'clock, when they normally all went home for the day, just in case they would be looking at the console or something when we did something wrong. Then we proceeded to use that shell injection attack, the double quote problem, to try to run commands on the server. And my grad students did some amazing things to make this happen. They built basically a virtual shell that would execute commands for us by automatically generating ballots with names and posting them and redirecting the output back and everything. A lot of nice hacking going on. But it worked, and it gave us basically the same permissions on the server as the voting application software. So what do you think the first thing we did was? Change all the votes? No, the first thing we did was steal stuff, right? So the first thing a real attacker is going to do is collect all the information they can that might help them to get back into the system if they're suddenly cut off. Right? We're going to find the database credentials, other information about the system configuration, any keys we can find. After we did this, the system would never again, for the duration of this election, it's never again going to be as secure as it was before we got in, because this is stuff that is going to be invaluable to the attacker. The second thing we did was change all the votes. And so what we did was they were encrypted with a public key, which we had because we stole all the stuff. We generated our own ballots and encrypted them with the same public key and replaced the encrypted files with them. Our ballots, instead of any of the real candidates, we wrote in the names of evil artificial intelligence and robots from the movies and so forth. Who would the computer have voted for if it was in charge? So because the files were encrypted, someone just examining the system wouldn't know that anything had changed until it was time to count the votes, which would then be too late. The next thing we did was rig the system to replace any new votes that would be voted later. We were able to modify the Ruby source because of the file permissions. So we were able to add functionality to do that. We also added a backdoor that after replacing any new votes, the system would also let us know what the voter's real intent was so that we'd both violate the secret ballot and the integrity properties of the system. Finally, after basically violating all the security properties, we tried to hide our tracks. We cleared the logs. We removed all the traces we could. But I, at that point, became a bit concerned that we had done too good a job. Because the real election now is going to be about a week or so later, 10 days later. And the trial wasn't scheduled to end until maybe less than a week before the real election. How were they going to? So there was some urgency to making the problem known. On the other hand, this was probably the best experiment we could think of to test how well real election officials could detect and respond to a realistic attack. So we didn't want to just go out and tell them. We wanted to let them somehow discover it so we could observe what the recovery process was like and learn something from it. So we compromised. We left a calling card. So our calling card was here in that thank you page that invites you to tell people you voted on Facebook and Twitter. We added these 3 lines. So after a few seconds delay, what this does is it starts to play the University of Michigan football fight song in an infinite loop on the voter's computer. Despite this change, it was more than 2 days before the election officials noticed anything was wrong. And they only noticed anything was wrong after another person testing the system wrote into them and said, hey, the system looks good to me, but I don't like the music that plays at the end. It's too distracting. Yes. Oh, and there was one more thing, though. One more thing. And I promised to finish quickly, but there's one more thing, which was that while we were poking around on the system, hacking it, we noticed a series of temporary files that were left around in the directory where the ballots that were uploaded were supposed to be. And some of these were predating the start of the election test. They were internal testing files left over. Someone in the hours before opening the trial to the public had been uploading other things to make sure the system worked. Some of them were ballots. Some of them were files that must have been uploaded to make sure the system would reject them. There was maybe the installation file for some code editing program. There was the manual to some Mac utility. Then there was one other file, which was a really, really big file. In fact, it was a 900-some page PDF file, the first page of which looked like this. So it turns out that this was the mail merge of the actual letters they sent to the actual voters with their actual credentials. Someone testing the system just looked around on his desktop for a PDF, happened to pick this one that has all the voters' real secrets, and uploaded it to the server that they asked the world to hack into. You know, just looking for any old testing doorstop, he found this. So they had given us, and given anyone else who hacked into the system, all the real voters' credentials. There was no way anymore that the system could be operated securely because you couldn't mail new credentials to the voters before the election would start. So this was sort of the final straw in how bad this failure could get. Washington, D.C. very wisely decided not to use their internet voting system for ballot return in the 2010 general election. Instead, they did something that seems to me like a very simple technical compromise. They allowed voters to download blank ballots with this system and then mail them back. That way, there wasn't going to be a central point of failure in the return process. There wasn't going to be the possibility of someone hacking into the server and changing all the votes. You'd have a piece of paper come back in the mail, but it would still cut in half the round trip time to send a ballot to the voter out in the field and get it back. So they achieved a lot of their goal with much less technical risk. Okay, so what do we learn from this? First, web applications tend to be brittle today. Just the standard web architecture has this problem, that a small mistake can have very big consequences. And generally, we deal with this by correcting the mistake, resetting the system, restoring from backup, and moving on. You can't do this in an election system during an election. You can't lose votes. You can't shut down the system for a long period of time. This is outside the requirements. Standard practices for engineering software don't seem appropriate for engineering voting systems. These are critical systems. If we're going to apply engineering practices, they have to be the engineering practices we use for things like the space shuttle navigation software, not things that we use for stuff like Facebook. The voting officials were not well equipped to detect and respond to problems. I mean, just think, in recent years, Google, Facebook, the Pentagon, have all suffered massive computer breaches. And these are organizations with very large IT response teams and a lot of security infrastructure. How are election officials who are not the Pentagon or not the NSA going to respond to that kind of challenge? I think there are really deep security challenges left to solve, especially in online voting. Things like protecting clients against malware, protecting servers against state-level intrusion, protecting users against phishing and social engineering attacks. And I think until we have good answers for these problems, which are some of the most persistent problems in security, we're not going to have a good answer for internet voting. That's why I think, personally, that it's going to be decades, if ever, before we're able to vote online with a high level of security. All right, I think I'll stop there for this segment of the talk. Thank you very much.